having understood total stress, strain rate, Newton's law of viscosity by going back and forth between solid mechanics and fluid mechanics, now we are ready to derive the Navier-Stokes equation. We have gathered all the background knowledge. So, writing Navier-Stokes equation or almost writing the Navier-Stokes equation, just 2 steps or 3 steps of derivation, and we will be at the Navier-Stokes equation. And in terms of our journey to the Navier-Stokes, of course, very obvious, we are at the last station, namely writing down the Navier-Stokes or deriving the Navier-Stokes equation using the stress strain rate relationship just derived. Okay. Of course, for a change there is no outline. The reason is there is only one line, which is Navier-Stokes equation. Okay. So, let us do that. What is the starting point? The starting point is the linear momentum balance equation. Okay. Just to recall, we were here for quite some time, I would say, okay. And now what we needed was just a stress strain rate relationship, okay. And that only we went to solid mechanics, understood strain, came to fluid mechanics strain rate, went to solid mechanics, understood stress strain, came to fluid mechanics stress strain rate relationship. So, all this was done to express stress in terms of strain rate, and now that we have achieved, now we can substitute that here to get this Navier-Stokes equation. Okay. So, our starting point is the linear momentum balance equation. Of course, there are 3 equations, one for each direction. Let us write down the equation for the x direction. Just to recall, left hand side you have transient term, the convection term, right hand side you have all the forces, the body force because of gravity, and then you have surface forces, namely pressure, and then the viscous stresses. Okay. So, now we will have to express this tau xx, tau yx, tau zx in terms of the strain rates or the velocity gradients. Okay. So, we will use the Newton's law of viscosity, which is a constitutive equation. Moment when at this stage of linear momentum balance equation, it is an exact theoretical equation. Okay. Of course, in terms of body forces, we have included only that due to gravity. Other than that, there is hardly any assumption. Of course, the viscous stress tensor is symmetric, even that is almost universally valid. So, in that way the linear momentum balance equation is a theoretical equation. Moment I go to the next step, so many assumptions have to be made, that has to be emphasized. Okay. Homogeneous, the next equation which are going, moment I substitute Newton's law of viscosity, that equation is applicable only for homogeneous, isotropic, linear, viscous fluid. Okay. That has to be kept in mind. On top of that, we are going to restrict only to incompressible flow. The Newton's law of viscosity, what we have written, there was a term for compressible flow as well, but we are considering only incompressible flow. So, one more assumption added to the above list. Okay. So, now let us write down the Newton's law of viscosity for incompressible flow. Okay. What are the we had 6 equations, we require only 3 of them, because there are only 3 components appearing in the x direction linear momentum balance. What are they? Tau xx, okay. And because this equation has been written for the x direction, what you have is tau yx. Now, of course, we know that tau yx is equal to tau xy, and this is the relationship between tau xy and the velocity gradients. Of course, we have tau zx. Okay. So, out of 6 equations, we require now only 3 of them. So, now what we will do, take the 3 terms which represent the net viscous force per unit volume on the right hand side, and then simplify, because all other terms there is nothing to discuss, nothing to simplify also. we will have to take these 3 terms, substitute the Newton's law of viscosity and then simplify. Let us do that. They represent net viscous force per unit volume. Okay, so let us write down them and then substitute. Okay. So, what is that I have done? For we have dou by dou x here, for tau x x I substituted 2 mu dou v x by dou x, and then I have dou by dou y of tau y x. So, dou by dou y substituted this expression here. Similarly, the third term. Okay, so let us simplify this equation. So, same equation is being written here. In this equation, mu is inside the spatial derivative. So, this equation can account for spatial variation of viscosity. Why should viscosity vary as a function of space? Because of probably change in temperature. Okay. But now we will make one more assumption, that viscosity is a constant, so that I can take this out of the derivative, which means that the equation which I am going to write after this cannot be used if viscosity is varying as a function of space. So, let us take out mu, then let us expand the derivatives. So, I have 2 dou squared V x by dou x squared. Let me write that as dou squared V x by dou x squared 2 times. Okay. Let us do this differentiation as well. So, first term is dou squared V y by dou x, and then this term gives you dou squared V x by dou y squared, and then we have dou squared V x by dou z squared, and then last term is dou squared V z by dou z dou x. Okay. So, now let us collect few terms together, all the terms highlighted in blue. So, let us collect these 3 terms together, okay. And then from the remaining terms we will take out dou by dou x, and what is left out are these 3 terms, dou v x by dou x plus dou v y by dou y plus dou v z by dou z, of course, which is the divergence of velocity field, and we are considering incompressible flow, which means this is 0. So, we are left with only the first 3 terms alone. Okay. So, the 3 terms which represented the net viscous force on the right hand side get simplified to this term. Okay. So, it is only matter of replacement, the left hand side is same, okay, and right hand side the body force and the pressure term is also same. Earlier we had the in terms of derivatives of the viscous stresses, and now we have simplified them to this term. So, those 3 terms on the right hand side have been expressed as sum of these 3 terms, okay. And similarly other directions, we know that we had linear momentum balance, one for each direction. So, similarly we have the Navier-Stokes equation also for one for each direction, okay. Of course, similarly for the z direction as well. Okay. Of course, that is Navier, that is Stokes here, okay. And of course, we can put in a vector notation. The left hand side we have dou rho V x by dou t, and these 3 terms can be put in terms of divergence of rho v vector V x. And of course, right hand side we have rho g x, gradient of pressure in the x direction, and of course, these 3 terms can be nicely represented as the Laplacian or del squared of V x. Okay. So, that way this equation is more compact. How to understand this? If we had rho v x, rho v y, rho v z alone, then it would have been divergence of rho v vector, that is what appeared in the continuity equation or differential mass balance equation. We have an additional V x here. Okay. Similarly, we can write in the other directions, y direction and z direction. Okay. And now we can compare the differential total mass balance and the linear momentum balance equation. That is a differential total mass balance equation, and the differential linear momentum balance equation in terms of the Navier-Stokes equation is what I have derived just now. So, to compare, we have the transient term here, here again we have the transient term, and we have here the convection term, here also we have the convection term. Of course, there the terms were for mass, here it is for momentum. Right hand side we had just 0 for the case of mass balance, but here we have all the forces, the body force and the surface forces. Surface force due to pressure and then viscous stresses, okay. And that is the comparison between these two, and we will build on this slide after we derive differential balance for energy and then species mass also, okay, so that all equations can be compared. Okay. Okay. The Navier-Stokes equation can also be put in the material particle viewpoint. We have already done this for linear momentum balance. What we have done earlier is the right hand side, when it was in terms of the viscous stresses for the linear momentum balance, we took the left hand side expressed in terms of capital D by dt. We have already done that. To tell you in short, we just expand, we just use product rule and express all the derivatives, okay, and collect terms in terms of rho and then V x, and this is a continuity equation. So, this goes to 0 and this is capital D V x by dt. Okay. So, left hand side becomes rho d V x by dt, right hand side of course, there is no change, okay. And this is a more popular form of Navier-Stokes equation, okay. Though we have derived in this way, the left hand side with rho d V x by dt is a more popular form, okay. And in vector notation you can represent still more compactly. We have rho d v vector by dt, instead of rho g x we have rho g vector, and instead of minus dou p by dou x we have minus gradient of p, and of course, here nu we have mu del squared v vector. So, very compact notation of the Navier-Stokes equation, okay. So, rho d v vector by dt is equal to rho g vector minus gradient of p plus mu del squared v vector, and x component of this is what is written here. Okay. Of course, v is given by v x, v by v z, g by g x, g by g z. Gradient of p is dou p by dou x I, dou p by dou y j, dou p by dou z k. Okay. And to summarize, we have derived the Navier-Stokes equation. As I told you, with all the knowledge we have, it was just few steps to get the Navier-Stokes equation. We took the viscous stress tensor terms on the right hand side of the linear momentum balance, okay, and expressed those components of viscous stress tensor in terms of strain rate tensor or the velocity gradients. Moment we do that, simple few steps we could get the Navier-Stokes equation, okay. And in terms of our journey, we have reached the destination and we just discussed the last block here, which is Navier-Stokes equation, okay. Now, if you have a long journey, after you reach the destination you are happy, and of course, whomever you people you meet, you recall whatever you experienced through the journey. Okay. It could be several people. We can also see that here we met Reynolds, met somebody called stress, somebody called let us say pressure, Cauchy, we had somebody called strain, and then we had Hooke, Newton of course, and then Navier, Stokes. So, we learnt lot of them from each of these people as well. Or if you make this analogous to different places, maybe you went to several places, explored several places as you travelled, and so you wish to recall all this, and that is what we will do now. We will also recall quickly our journey. We have repeated this several times, I would say almost before every lecture and in between lectures as well. So, one last time we will go through this slide starting from beginning to the end, and at every stage we will have some few recall slides. Okay. That is how the summary is planned. Okay. So, let us start with the Newton's law of our system. That is where everything began. We applied the Reynolds transport theorem, and then we got the integral form of linear momentum balance. Okay. And here are the slides, just only few summary slides from each. So, this equation represents the Newton's second law of motion for a system, rate of change of momentum, sum of forces acting on the system. We applied the Reynolds transport theorem. So, the left hand side was expressed in terms of a transient term and a convection term for the control volume. Right hand side was still in terms of system. We took a coincident system and control volume. So, right hand side became that for the control volume, and that is the integral form of linear momentum balance equation. Okay. So, we were here. Now, what did we do? We took a small control volume, applied the integral linear momentum balance for a small control volume, and obtained the differential form of the linear momentum balance, the left hand side and gravity on the right hand side, and that is what we will see now. We took the integral form of linear momentum balance for a small fixed control volume, and then expressed the transient term and the convection term as applicable to this small control volume, and obtained the left hand side of the linear momentum balance, the transient term and the convection term. Now, we also on the right hand side we had the body forces and the surface forces. At that point of time we discussed only the body forces, that due to only the gravitational effect, and then we discussed the body force as rho into g vector. Okay. So, at the end of this we were here, the differential form of linear momentum balance, the left hand side and gravity on right hand side. We need to understand the surface forces, we need to express them. Understand that we took our first diversion to solid mechanics, we discussed this block stress vector and stress tensor. So, few slides from there. So, the stress vector and the components of the stress tensor. Then we related these two, the stress vector to the components of stress tensor using the Cauchy's formula. Okay. So, we completed this block, we extended this knowledge to fluids, then we discussed these two blocks, total stress, fluid under rest and pressure and viscous stress tensor. Some slides from here. So, once again stress vector, but now components of total stress tensor in terms of capital T. Once again we related stress vector to components of total stress tensor by the Cauchy's formula. Then to proceed further, we discussed the difference between solids and fluids. We said fluid under rest cannot sustain shear stress. Based on that, we discussed the stress in a fluid under static condition, which is normal stress, which is pressure, the thermodynamic pressure and it is compressive, hence minus P. So, we got the component of total stress tensor under hydrostatic condition. So, we express total stress in terms of hydrostatic stress and a viscous stress. So, that is what we discussed here, fluid at rest, total stress tensor in terms of pressure and viscous stress tensor. Having understood the surface forces, we substituted here and then completed the differential form of linear momentum balance. Gravity was already discussed. We included pressure and viscous stress on the right hand side and few slides from there. So, now our attention was on the surface forces, specific attention was on the surface forces. We expressed the surface force for pressure and for the viscous stress, and then we combined with our earlier transient term, convection term and the gravity on the right hand side. Along with that, we included the surface forces due to pressure and viscous stresses represented by all these four I would say control volumes, and then we derived the complete form of the linear momentum balance. I would say we completed the linear momentum balance. Till this point we already derived these two terms, or these two set of terms were newly added. Okay. At this stage we were here differential form of the linear momentum balance with gravity, pressure, viscous stress on the right hand side. Look like we are almost there, but then we will have to know more to proceed further. It is like reaching a big station and one station before you are put for a long time, you do not get a signal to proceed further. Something like that we are there. What was the objective? We did a degree of freedom analysis and found that the viscous stresses are not known, they are unknowns. We will have to express in terms of the velocities. Of course, now we know the velocity gradients. Okay. And then we took a second diversion to solid mechanics, discussed about normal strain, shear strain, expressed them in terms of the displacement gradients, the normal strain in terms of displacement gradient, the shear strain in terms of displacement gradients. And more importantly, we discussed that the displacement gradient tensor a sum of strain tensor and rotation tensor. And we also said that the stress tensor has to be related to the strain tensor. Now, at that point we have completed these two blocks. We will have to extend that knowledge analogous to fluids, where we discuss the strain rate and strain rate tensor. Okay, few slides from there. We once again discuss the difference between solids and fluids to understand that it is strain for solids and strain rate for fluids. Force depends on strain for solids and force depends on strain rate for fluids. And we discussed normal strain rate and shear strain rate. We said they are material derivatives of normal strain and shear strain, and then we related the normal strain rate to velocity gradient, shear strain rate to velocity gradient. And once again, more importantly, we discussed the velocity gradient tensor as sum of a strain rate tensor and rotation rate tensor. Once again, we said the objective is to relate viscous stress tensor to the strain rate tensor. Okay. So, at that point we have discussed these two blocks. Now, having understood stress and strain and viscous stress and strain rate, next step was to relate these two for solids through Hooke's law and for fluids through Newton's law of viscosity. So, once again we took a diversion to solid mechanics and discuss the assumptions now, because they are material dependent, and came back to fluid mechanics, just wrote down the Newton's law, and all those are summarized in one slide here. Hooke's law of solids, assumptions, and for Newton's law of viscosity and the assumptions here. And these 6 equations represent Hooke's law. By change of variables we obtain 6 equations representing Newton's law of viscosity, and that point we had completed these two blocks. So, now it is a matter of substitution of this here and obtaining here, and that is what we have discussed just now. Took the linear momentum balance equation and then substituted the Newton's law of viscosity, few more assumptions we made and obtained the Navier-Stokes equation, okay. And that we reached the destination. Okay. It has been a long journey, and that is why it has been called as journey to the Navier-Stokes. Also like to mention that usually derivations are considered boring. Okay. Now, we have seen a derivation, we can say that we have been deriving from Newton's law to Navier-Stokes over several hours, several lectures. A derivation can be as challenging, as interesting, as knowledge gaining as we have seen. Okay. We have learned so many concepts, so many assumptions wherever required, and so derivation helps to know the scope of application of a particular equation, and once we derive, you also know the physical significance of each of the terms in an equation. Otherwise, there is some term, the dou V x by dou x, but now if you look at dou V x by dou x, you know the physical significance of that particular term. Okay. Similarly, all other terms in the equation. Okay. Those are the advantages of doing a detailed derivation. Fundamentals becomes very strong. Okay. So, now we will have to look at applications of the Navier-Stokes equation, okay, which we will discuss in the next classes.